we're continuing on section 14.6, and this time related rate and multivariable chain rule. So this is something we saw in calculus 1. This example is the volume of a cone, v equal to pi r squared h. That's a formula where r and h are the radius and the height of the cone. Both r and h are changing over time. What is derivative of v with respect to time at an instant where r is this, dr dt is 3, h is 6, and dh dt is -3. And so according to the chain rule, first of all, v is a function of r and h. So according to chain rule, derivative of v with respect to time is equal to derivative of v with respect to r times derivative of r with respect to t plus derivative of v with respect to h, derivative of h, the partial of v with respect to h, derivative of h with respect to t. And so from here, this one I have to compute. This is going to be pi 2 pi r h divided by 3. This one I have to compute. Derivative of v with respect to h is pi r squared divided by 3. Now I have to plug in. So when you plug in for r, you plug in 5, for h you plug in 6 divided by 3 times dr dh dt, which is 3, and so 3 plus pi 5 to the power 2 divided by 3 times -3, and then you all add them up, and the answer is going to be 35 pi. Now, implicit differentiation in multivariables. How does this work? If you have z equal to z of x and y, and you put all the variables in one side equal to a constant or 0, then we can use the chain rule to find the implicit differentiation. So we had methods from before. Now you see the new method basically. And so here let's start the f of x and y, and z on top, then go x, then go y, then go z. Z is a function of x and y. So when you're trying to find the derivative respect to partial respect to x, you go these two routes, and that is so you're finding basically, then this is equal to c, so you're finding dc dt equal to, this is f sub x, and this one is f sub z times z sub x. But dc dt is constant, c is constant, so it's 0. So if I want to find z sub x, that would be negative f sub x over f sub z from solving this equal to 0. And then let's try to find everything. Negative f sub x, negative f sub x over here, f sub x, that's f, and finding the right side, the left side is f, and f with respect to x is going to be equal to, the negative sign stays, and z squared plus y, and then the bottom f sub z, and that would be 2xz plus y squared, and it's as easy as that. Just the formula every time you can find the formula and solve. But if you, in the past, when you were when you were doing the implicit differentiation, then you had to do a product rule here, then recognize that only z and x is the independent variable, z is going to be depending on x, and y is going to be constant. So when you did the chain rule, you would get rid of y sub z everywhere. I'm sorry, not chain rule, product rule. You would do that partial with respect to x of y is going to go away because y is an independent variable. Then you solve. You have to keep track of a lot of little details, and then you would solve for z sub x. Now this method makes it a lot easier, and you get the same answer anyway. So again, implicit differentiation, multivariables. If z is equal to z of x and y, as defined implicitly by an equation f of x and y and z equal to c, then general formula, which we can you can memorize if you want to do so, are partial of z respect to x is equal to negative f of x f sub x partial respect to x of f at x, y, z over partial with respect to z of f of x and y and z. So if you, when I memorize this, I go, oh, that's a z over there, and z over here, x over here, x over there. So it's kind of diagonally going, and there's a negative sign in there. And for partial of z respect to y, and similarly again, the partial respect to y appears on top, and partial respect to z appears in the bottom, and there's a negative sign. You don't need to memorize these formulas since they are both come from the same process, that the chain tree that we use. And also observe that the partial of z with respect to x and partial of x with respect to z are going to be reciprocal. And the units in this formula make sense too. And that's another thing to notice, because that's why you saw that kind of diagonal shape going on too. And so that's another thing to remember, that there's a diagonal shape going on. So again, this is exactly the process that we did to find basically partial of z with respect to x. We started from c on top, and we wrote down, and one side was 0, and then we solved for partial of z with respect to x, and that was the formula. And then if you want to do partial of z with respect to y, again you write the same, you draw the same tree, and in this time you solve for partial of z with respect to y, and that's the other formula. The implicit differentiation in multivariables. What is this? The example 5, what is the slope of the surface given by xy squared plus x to the third z plus z to the third plus 1 equal to z to the third plus 1 at the point 1, 1, 0 in the direction given by the unit vector u equal to 3/5 and -4/5. Directional derivative, we need a gradient vector. And the gradient vector, this is an implicit surface, and the gradient vector to the implicit surface is going to be z sub x and z sub y. First coordinate z sub x, second coordinate z sub y. So it's an implicit differentiation. Again, let's write the formulas, and first of all, let's find f of x and y and z. To find f of x and y and z, you have to take all variables to one side. So taking all variables to one side, Then find f sub x. This is f. X and y and z. So f sub x is equal to y squared and plus 3x squared z. F sub y is equal to 2xy, and that's it. F sub z is equal to 3x squared, 3x squared, sorry, 3x squared minus 3 not 3x squared, but just x to the third minus 3z squared. And now let's find out each one of these f sub x at point 1. What was the point? 1, 1, and 0. It is going to be equal to 1. F sub y at point 1, 1, and 0 is going to be 2. F sub z at point 1, 1, and 0 is going to be 1. Now compute z sub x according to formula, that is equal to negative f sub x divided by f sub z. F sub x divided by f sub z. That is f sub x divided by f sub z, negative 1, and then z sub y is going to be negative f sub y over f sub z, and negative f sub y is negative 2 and divided by 1, so this one is negative 2. So the gradient vector is negative 2 and negative 1. And then dot product that with 3/5 and negative 4/5, and that comes out as negative 6/5 minus plus 4/5, that's negative 2/5. So the gradient vector is negative 1 and negative 2. Now multiply that by dot product 3/5 and negative 4/5. That's the vector, the direction vector, and that gives you negative 3/5 plus 8/5, which is 5/5 equal to 1. Therefore, the directional derivative in direction of 3/5 and negative 4/5 is going to be 1.